Okay. Just to practice the first part of the lecture, let's have a very simple example in MATLAB. So assuming that we have time to be 0 and with the frequency of 1 kilohertz to 4 seconds. Then we define S1 to be pi times 200 hertz times t So if we plot S1, we see nothing. So let me, it's too much samples. To 1 second. Okay. Let me make it 20 hertz. So it's clear now. So that's a signal S1. Then I do a trick. I use S2 to be 20 samples 10 samples delayed version of S1. Now both sides are the same, and if you plot S2, that's just a delayed version of S1 for 20 samples. Now if you calculate the cross correlation between S1 and S2, and then if you plot the result of the cross correlation, you see such a thing. For 10 samples, they are pretty much, the correlation it's just 10 samples difference, lag in the time. So when it comes to 10 samples, for the frequency of 1 kilohertz, it's actually getting the maximum here, and it reduces again. So it's a symmetric function, and it has a peak in some value. Now if you take it as a random signal, for example, if you assume that S1 is, let's clear all. Assuming that S1 is a random signal generated from a random Gaussian noise, for example, for, 200 samples, and S2 to be 40 samples delayed version of S1. Then if you calculate the cross correlation between the two and you plot it, so let me use the subplot. And you see here that you have the S1, a random signal taken from the random Gaussian noise with variance 1. We have 200 samples. And here we have S2 is just a delayed version of S1. So we have 0 beforehand, and from here it starts exactly the same as what S1 started. So it's just a delayed version of S1. If you calculate the cross correlation between these two signals, if you assume it as two different signals, then it's a cross correlation. Otherwise, if you assume that it's just one signal and itself with the delayed version of itself, so it's an autocorrelation with some lag. Then you see that there is a peak here. And that peak is actually the point that should actually represent the amount of lag that it has between these two, this one and this one. So that was a simple example of autocorrelation or cross correlation using its core, or we have also cross correlation, and you can find them in MATLAB help menu. Okay. Okay, let's start with the next part of the statistical DSP. What I'm saying is actually a completely brief and succinct version of what SSP is. SSP is a course. What I'm telling you is actually giving you the leads and also some rule of thumb methods that you can simply leverage when you want to do simple projects. But it's not necessarily meaning that if you go through reading a paper or a journal paper or a book, you can understand everything, because there are a lot of theories missing. So in general, you will get familiar with the terminology of SSP and some very important and very prevalently used techniques. And that would be a good lead for you to actually follow up and continue studying the SSP stuff from the materials, the books and tutorials that you might find in the internet. So this lecture I'm going to talk briefly about estimation theory as an introduction, and what are the categorization of the problems and the subjects under the umbrella of estimation theory. Just gives you the leads. You will understand how to put your problem into which kind of category after this lecture. The same thing for the optimization. So you will understand what kind of optimization you're actually encountering in your specific problem, and what kind of category you have to choose if you want to solve your problem. In the coming up lectures, in the next days, we will actually encounter some very trivial examples of estimation and optimization problems. And we don't want you actually to be able to solve the problems on the paper, even using the, for example, the MATLAB codes. You can implement that if you want. Otherwise, you can just make use of the toolboxes. And I will never ask you in the exam about that. So I just say, explain a problem in details, but when it comes to the optimization or estimation, just you can copy and paste whatever it was in the lectures. And if it's something necessary, I will put it in the exam paper so you can have it. And you don't need to go through the detail of theory, proving something. Okay, let's start with the estimation theory. After talking about the random signals, probabilities and random signals and random processes actually. The first thing that comes up is, okay, if we're dealing with kind of random process, then probably we need to model that process, and those models usually they actually come along with a lot of parameters. How can we estimate those parameters in order to create a kind of generative model or a discriminative model to solve our problems with? So, as a very simple example, we have an observation, a signal as an observation, and this signal is naturally distorted, corrupted by the noise, reverberation, fading, interferences, whatever corruptive effect that it might be in the environment. And then we receive it in the receiver by any sensors. The point is that that signal in the receiver as an observation, which is corrupted and noisy, is a function of some clean signal that we don't know it. We call it as theta, the parameter that we are actually looking for, and a noise of the environment which has a different essence from that signal. So we know that signal is coming from some source, but that noise is whatever we don't know anything about. We just put it in the category of noise. So x as observation is a function, h in general as a function over parameters which we are looking for, the desired parameters, which are theta in general as a vector of the parameters. It can be a list of parameters that we are looking for, or just a single scalar value, and a noise, which we generally name it as n, as a noise. Now the point is that what we are looking for is not noise and is not the observation. We are going to use the information we can get from the observed data and the noise to get the parameters, to estimate those parameters, which are theta parameters. Any kind of estimate that you make is finally called theta hat. So theta hat is your estimate about the parameters of the model, and the entire thing is called a model. Model is something that contains your signal and your system. Now the point is that, well, any kind of function that you use, maybe you're just using a g function as something like an inverse function of h in order to get the parameters, estimate the parameters. Then g is an estimator. Estimator which uses the observed values to get the parameters as an estimate. In general, those estimators are not only dependent on the observation values, but also they are dependent on the length of observation data. So we have to take care. It's not like that we can take a look at the data for forever. We have just the limitation of the data size, for example, for some seconds, for some minutes, for some hours or days. And then we have to estimate the parameters out of that data. The memory is limited, so we can just grab the data for a while and then start making estimation about the parameters underlying that data. So we have the length of observation, which is also important. In all the estimators, it's one of the other parameters that the estimator depends on. The second thing is how you're looking at the process. So the process model is also very important. So there are two other hidden parameters that you never see it, but they actually exist. And it's a kind of condition that the problem actually imposes to you. That's the general definition of estimation problem. Now, we have to make a strategy how to go through the problem, how to solve that. There are two different views to solve any kind of estimation problems. One of them is based on the idea that anything that we don't know it is unknown, but not necessarily probabilistic. So we say that parameter or a signal that I'm looking for is something that I don't know it, but in general is something deterministic. That's how we look actually to the problem in the frequentist view. Something that naturally happened during the last decades. For the techniques that coming under the umbrella of frequentist view, they are actually implicitly thinking of some kind of repeatable experiment, a kind of experiment which can be repeated several times, and then you can count the number of outcomes, and based on the number of the outcomes you can assign a kind of probability to that event to occur, that desired event that you're looking for. So there are several techniques, and what I have written here is just piece of those techniques as the most prevalent methods that are used. And starting from minimum variance unbiased estimator, I'll explain just the intuition behind what MVUE actually desires, what's looking for. Then we talk about the best linear unbiased estimators, maximum likelihood estimator, which actually in most cases we use actually the maximum likelihood estimation method, and the least square estimators, which is very prevalent specifically in the adaptive filters. When we come to the adaptive filters, you'll see that least square is one of the methods. The second view says that not necessarily everything is repeatable, but naturally what it comes with something that we don't know is that let's take it as something, because we don't know it, we take it as a random variable. We take it as a random variable, and we say that the signal itself is a random variable, the observation that we take is a random variable, the parameter which we don't know is also a random variable, and whatever we don't know it is a random variable. As a consequence of being a random variable, we need to have a probability assigned to that. Every random variable has its probability distribution. It has to be taken from some kind of distribution, and how we can deal with these kind of distributions to get the parameters that we need. Then different approaches come as the techniques under the umbrella of Bayesian views, the Bayes theory and the Bayesian or the Bayesian view for the methods that come as the Bayesian estimators. The most prevalent one, which I have dropped one actually here, one is the MMSE estimator, minimum mean square of the error estimator. Is pretty much the same as least square estimator in the Bayesian view. So you can make equivalence in your mind that MMSE estimator is quite the same as LSE in the Bayesian view. Then we have linear MMSE estimator, and the most important, I forgot here, I dropped it actually, it's a map estimator, maximum a posteriori estimator. But I will explain in the slides, even though I dropped here. So we have these two different views, categories, and all the techniques that come afterwards. The first step we have to take is that we have a data, and we know that this random data, this signal, corrupted signal, depends on kind of parameter. We have to look for a PDF, a distribution for this random variable. A PDF which can be represented as probability of, or in general a probability function of random variables, random variable x, given something as a parameter which we don't know it. And if you take the Bayesian view, you also assign a kind of PDF to that. If you take the frequentist view, you don't assign a PDF to that. But in general, you have such kind of PDF for the data itself, because data is random. Doesn't matter whether you're looking frequentist or a Bayesian. Data itself is a random thing. In the first approach, the frequentist approach, so we have this MVU, MLE, maximum likelihood, or the linear estimator, and this kind of methods. And in the Bayesian view, when you have both the data, observed data, and the latent data, or the hidden data, something that you don't see it, when both of them are random variables, then you can have joint random variable, joint probability distributions. So you have the probability distribution of joint process, joint random variables, which is the observed one alongside with the unknown one, the one that you desire actually to get it. And we know that based on the probability theories, you can use the Bayes theorem, the sum and product rules. These are the rules come in handy when you're dealing with the probability. Sum rule, product rule, and the Bayesian equation. These are all three things that you need. And there are some definitions. So when you have the joint probability distribution, so it's called joint probability. If you have the data, observed data, when you say that the probability of this observed data being taken from some known theta value, then it's called the likelihood, and it's a function. It's never probability, because you assume that theta is already known, something that is random, it's hidden, you assume that it's known, and you're actually looking for how likely is that this data be taken from that theta which we assume to be known. It's a likelihood function, and whatever your idea, your prior belief about those unknown values, you can put it as a probability of priors. So you call it as prior, and P is actually here. P is actually P of theta is your prior, and prior is nothing but your belief. You know in advance, before going to the problem, you have some belief about that prior and how it might happen. What should be the approximate PDF that this prior, this theta, this unknown variable, latent variable should be taken from. That's just your belief before you observe the data. And when you observe the data, then this prior changes to posterior. So P of theta is prior, but P of theta given x observed is now the posterior. It's not prior anymore, it's posterior. The domain of search is actually more limited because you have observed something out of your belief. Part of that domain of the belief would be thrown away because you have observed something. Now you're getting more narrow in your belief. And P of x given theta, which is actually a function, it's not P, it shouldn't be written as a form of the probability, but we actually forming it like that, is called a likelihood. How much it's probable or likely that this observation x is taken from the theta, some theta which is known. So it's a function over the theta values. So these are the definitions, and for the Bayesian case, we have nice algorithms like the MMSE, as I told you, the map, maxima posteriori. And we have a technique which uses the iterative Bayesian estimation. If it's linear, then the iterative linear Bayesian estimation is called Kalman filter. It's just the other name. So the Bayesian linear iterative estimator is called Kalman filter. And when it's partially linear, then it's called extended Kalman filter. When it's nonlinear, it's called unscented Kalman filter. And when there is no model, there is no probability assigned to the data, then it's called particle filter. So there are some desired estimator properties. So these are the properties that we desire to have actually for any estimator. The first is we desire our estimator to be unbiased. It means that we desire that the mean of the estimation to overlap with the true mean without any deviation. So here, theta is actually, can you see it? Okay. The theta is a true mean value, the true value. The estimator A has its mean here just overlaid with theta. So it means that it's an unbiased estimator, even though its variance is much more than estimator B, but it's more preferable. Why? Because estimator B actually has its mean value pretty much deviated from theta, even though that estimator has less variance, but the probability of getting the right value is much less. So we prefer to have an unbiased estimator. An unbiased estimator that estimates the mean as the true value. And that's the expectation as the mean. We know that expectation is nothing but the mean. So the mean of our estimate should overlap with the true mean. Another desirable property is to be efficient. We need, or we desire actually, our estimator to be efficient. The efficiency means that the variance of our efficient estimator should be less than the variance of any other estimators. As an example here, we see that, for example, if this one is our estimator, this has the minimum variance among all other estimators that we have. And the final one, which is also shown in this figure actually here, this curve, the consistency, which means that if the number of the samples that you take it to make that estimate, if the number of the samples goes to infinity, the variance of the estimator goes to 0, and it becomes something like an impulse. When it's impulse, it means you're certain about your estimation. And naturally speaking, when that window size, the number of the samples that you can leverage in order to get the estimate of that unknown parameter, if n number of the samples goes to infinity, it means that you should have all the data, information about that unknown parameter. So you have to be able to make that estimate completely without any deviation. So it means that it should finally, in the limit, be something like spike, something like an impulse. And that kind of estimator, which by increasing the size of the estimation window, reduces the variance, and in the limit it goes to the variance goes to 0, is called a consistent estimator.
So in the first example, we have estimator A is unbiased but is not efficient.
It's unbiased, but we don't know about the efficiency, because we have to know that what are the variances of the other estimators, which are also unbiased. If
with X estimator B is not efficient because the variance is bigger in the estimator A
the consistent,
rather than estimator B.
yeah, these are the independent notions actually. So unbiasedness, efficiency, and consistency are independent notions.
Okay.
So if you can find a kind of estimator having all three desirable properties, it's a piece of cake. So it's the thing that you just needed. Otherwise, then you have to it's a trade-off. Which one you have to take? People in the community say that go for the one which is unbiased and has the minimum variance. And that's called MVUE, or the minimum variance criterion based estimators. So they say that, let's talk about the minimum variance. When we say minimum variance, it means that your estimate, the difference between your estimate and the true estimate is called an error. Energy of that error should be minimized. That's called the minimum variance. The criterion of minimum variance just means like that. The error between your estimate and the true value, this is the error. Square of the error is just the energy of the error. Expected value of this should be minimized. That's MSE, minimum square of error.
In this case, do we need to take into the unbiased
We will come to that. Just I use the minimum variance criterion.
yeah.
Then when I explain the idea here, which is in the black rectangle here, when I explain that, then we say that finally we come at minimum variance unbiased estimator, MVUE. We're looking for such kind of estimator as the best estimator we can make. And then we see the problems, and then in order to dissolve the problem in such a way that getting good answer, reasonable answer, then we say that okay, MVUE is not applicable, is not something that you can get it actually in most cases, so we go through different approaches. But at the moment, so MSE, we define what MSE is, and then just replace the parameters that you have here. So by replacement, so you just add this term and this term. So add and subtract the same thing here. And then make this square happen, expand it. By expansion and definition of the bias, which is actually the true estimate, difference between the true estimate and expectation of your estimation, that's the bias, the definition of the bias. Then you come up with this equation that the MSE, minimum square of the error, is equal to variance of your estimate and the bias of your estimate. But the bias is square, so they have different weights. The bias is square and the variance. Okay? The dimensionality should be the same. Now it's based on the energy, and bias square is also based on energy. So they have the same dimensions. But what we can get from that is also in your machine learning. You see it in machine learning. In every estimate that you do, you have the same thing. What is the point? The point is that every estimate that you do, you're trying to, for example, come to a kind of error, 10 to the power of minus 6. That's your desire. For example, that's your desire, to come to the minimum possible error. 10 to the power of minus 6 is what is the threshold of the desire that you need for the error. This fixed error means variance or bias, one of them should take the advantage, because that's constant. And you have this plus this. So either you have to play with the variance and make the bias fixed, or the other way around. Which one? Which one you prefer? The point is that, you see, intuitively we see that bias is very important. On the other hand, we see that bias is important with degree of 2 compared to the variance with degree of 1. So bias is more important than variance. What we naturally do is to take the bias as minimum as possible and then play around with the variance to get the minimum possible variance. And the minimum bias is 0. So take the bias to be 0 and play around with the variance and try to get the minimum possible variance out of your estimation. That's called minimum variance unbiased estimator, and all the category which comes as MVUE. Without going through the MVUE, the Kramer-Rao band and Rao-Blackwell optimization methods and so on and so forth, which is a complete 10 sessions of the course. I'm going to explain some of the problems that come after MVUE. The problems that come is that not necessarily MVUE exists. So it's a kind of estimator that does not always exist, and that's a problem. You might find no estimator which is unbiased and gives you the minimum variance. And finding the MVUE estimator actually goes through 3 different things. One is that you have to define and determine the Kramer-Rao lower bound for your estimate and check whether you can find an estimator which satisfies this band to give you the minimum estimate, at least to be in the Kramer-Rao band. And these are the problems, and maybe you cannot find such kind of estimator for your problem. The idea is that, okay, let's go to a narrower kind of estimators, which we can actually have an estimation for that. So a kind of method which certifies that we can find an estimation. That's called the linear unbiased estimator, or the best linear unbiased estimator, abbreviated by BLUE. So using the fact that MVUE estimators does not always exist and sometimes impossible to find it, and also the fact that the PDF of the data may be unknown, we come up with the idea of BLUE estimators, best linear unbiased estimators. These kind of estimators, as it comes from the name, they are linear estimators. Linearity means your estimate, that G function that I explained already, G function is a linear function. When it's a linear function, then it's a linear function of observation. So your estimate is just a linear function over your observation. So theta hat is nothing but AX. So you're restricted everything from G as a general function, which might be nonlinear, to just the linear case, which is AX, a linear equation. Again, you need an unbiased estimator because of the reason that we explained in the previous slides. We need something unbiased. Then you apply to that, and you get the condition. Linearity together with unbiasedness gives you that expectation of the left-hand side should give you the expectation of the right-hand side, and A is just the parameter of the model, and expectation just applies for the random data, which is X, and we know that this is a true value. This should be the true value because of unbiasedness, and that's the result. Then you try to find such kind of estimator that gives you the minimum variance, but it's linear. And this estimator actually has this advantage that only needs the mean and the variance of the data and doesn't need the entire PDF of the data. Let's see an example. We have a signal x of n, and this signal has this kind of relation with the clean data, for example, s of n times some amplitude, theta, and there is an additive noise, w of n. Here we are looking for just the amplitude estimation. So we assume the only thing which is unknown is the amplitude of Sn. And we are actually looking for this theta. And this is the white Gaussian noise with zero mean and some variance. Sigma square as a variance. Because we are looking for blue estimator, so looking at the previous one, looking at this, we have the estimator to be A transpose X. Here we're talking about the scalar case, so A transpose X. Applying this estimation, this expectation over the estimate and the other hand side, we get this A transpose expectation of X to be theta, and expectation of X, what is it? So expectation of noise, because it's zero, it's a Gaussian with zero mean and some variance. Because of zero mean, expectation of this plus this gives us the expectation of this part plus expectation of this part. This one is zero, cancels out. This one, S is noun. The only thing which is unnown is this theta. So we have the expectation of theta times this one. So this is the entire thing that you should have. So it becomes A transpose, and this is your expectation value. Expectation of the left hand side is just this one, S theta. That's the mean. That's the mean. And you need this to be theta. It means that A transpose S should be 1. That's one of the conditions takes out just because of the properties that we have for the blue estimators. Now you want to minimize the variance. Variance A transpose covariance A. Can anybody say that how we could come up with this? So simple. Just instead of covariance, you see covariance is nothing but X transpose. In general, expectation or the sample covariance is X transpose, the vector of X times the transpose of the vector of X. If you just replace that, you see that A transpose X transpose A. And A transpose X is nothing but, and the other one is transpose version of that. So here, it's nothing but the covariance of estimate. We want the estimation to have the minimum variance or covariance, doesn't matter. So it means that the expectation of theta hat transpose should be minimized. And this expectation in the sample case becomes theta hat transpose. And theta hat is A transpose X, theta hat transpose is X transpose A, and X transpose, because theta comes out of the expectation. Theta is unknown, but because we are doing actually the frequentist view, we can take the theta out of the expectation. It becomes A transpose covariance of X times A. And just we see A transpose CA. That's what should be minimized. It's also called the energy of the estimate. That should be minimized, but we had already one condition, and the condition was that A transpose S should be 1. So the problem, the statement of the problems in the blue scalar case is that minimize this energy subject to this condition. Okay? And you're looking for the theta values. So we can change this problem, this constraint problem actually, to an unconstrained duality using the Lagrange multipliers. Probably you're familiar with the Lagrange multiplier, which actually helps in order to change the problem from the constrained version to the unconstrained version. And for this kind of convex problem, it actually gives the unique answer. Doesn't matter whether you go through the constraint or the unconstrained, the answer is the same. So our cost function is nothing but A transpose CA, covariance A, plus a Lagrange multiplier, lambda, times A transpose S minus 1, to make it as 0. And lambda is just a regularizer variable. Is a variable which makes the trade-off between this part and this part. The trade-off between these two is just by using this lambda variable. You solve this problem easily to get the values of theta by using the derivation of this cost function and just using the derivation, the optimal solution comes with this. So the optimal value, the optimal blue estimate of the theta comes like this. And this value in the denominator is actually somehow you're actually normalizing by the variance. So 1 over this is the variance of that estimate. S transpose inverse covariance matrix times S. That's your estimate in the blue scalar case. And we can generalize that to any kind of vector case. For example, here in the vector case, you have the X as a vector, H as the linear system, as a linear model, times theta, unknown variable we are looking for, and the noise, which is Gaussian. This can be a general model that, for example, in the case of multiple sensors, it can be applied, because multiple sensors means it means a vector of any signal. And this is something that you will see it in the beamformer. We will explain in the coming lectures. The values, just replace that whatever here was a scalar just with this vector version and you will get it. It's nice to know that if noise is Gaussian, then the blue and MVUE gives the same answer. They're the same. The most natural method, the technique under the umbrella of frequentist view is maximum likelihood. So you are actually having a function which is the likelihood function, the likelihood of this observation being taken from some given parameter values, theta. And if you get this function and maximize it over the parameter domain, the parameter set, the value that you get is actually the best in the sense of maximum likelihood. There are properties assigned to the maximum likelihood, and the most important thing about the maximum likelihood is that normally this is the conditional probability or the conditional function. The important thing is that normally we use the conditional probability of the data over the parameters. We actually take these probabilities or the likelihood functions as an exponential family. And they are mostly exponential families. Because of actually belonging to the exponential families, we have this ability to take the logarithm, and it simplifies everything. In order to simplify, we can just take the logarithm and we call it log likelihood function. Because in exponential form, if you take the logarithm, you're just working with the exponentials, not with the, so you're actually simplifying the multiplication to just summation. And we actually look for the log likelihood, and the answer is the same, because the logarithm is a monotonic function with respect to its argument. So if you get any answer for the likelihood, the same answer would apply for the log of likelihood. And the same thing happens. You have a problem. You want to get the maximization of the problem. To get the stationary point, after taking the log likelihood, to get the stationary point, what you have to do is getting the derivation with respect to the parameters, make it equal to 0, and get the parameters out. That's the log likelihood. That's the maximum likelihood estimate of your parameters. And it's interesting to know that there are properties for the maximum likelihood, but for the large data set, if you have a large amount of data set, then we can actually figure out that the maximum likelihood is actually the best answer. The best that you can get is actually the maximum likelihood if you have large amount of data. But if you have lack of data, the maximum likelihood probably is not a good approach to take. So one of the approaches that when you have the lack of data is applicable is Bayesian estimators. Bayesian estimators look at your problem as everything unknown should be a random variable. Because it's a random variable, you should assign a PDF to that. So theta is unknown and is a random variable. So it means that we need to have a theta, we need to have a probability distribution for theta together with x, and then we have the conditional probability distributions and the priors. Naturally, we are looking for the parameters given the observation, and that's called the posterior. So the probability of getting parameters given the data or the observation is called the posterior. And when you don't have the data, observed data, it's just the prior, or your initial belief about the parameters. So all the Monte Carlo methods actually trying to use the Bayesian point of view. Equivalently, we have the MSE as a Bayesian view. So the MSE as a Bayesian view is expectation. You see here is the MSE in a normal case, but here we have the MSE as a Bayesian MSE. So the definition of the problem, the error is the same. The only difference is that now theta is also a random variable. Because it's a random variable, so you have, here we just had the conditional distribution of x given theta, but here we have the x and theta as a joint distribution, and you have to integrate over the theta set of values. So that's the only difference in the definition of MSE in the classical case or frequentist case and the Bayesian case. So we make a linear estimate again in the Bayesian form. In the Bayesian form, we assign the observation, the equation for the observation or the model for the observation to be like that. So a linear function over the theta values plus some noise. But in this case, we have for the noise, we have zero mean, a Gaussian with zero mean, and a covariance matrix of the noise. This is the vector case. And for the theta parameters that we don't know actually and we're looking for, is also a Gaussian or a normal with some mean and some covariance. In order to solve the problem and to get the values, the unknown values, we need to calculate the covariance of the output and the input and output, or the unknowns and the observation together. So getting the covariance of x, you come up with this. So definition is like this: the expectation over x and the mean extracted out of that times the transpose of that. Replace every x with this equation here, and then apply the expectation to the cases, because here we know that for theta we have the mean like this. When you apply that, you come up with this, and this term would get out of that. For this one, which is noise, we know that this is the variance of the noise. You put CW. And for this part, H, this expectation, which is similar to covariance, H transpose, completely similar to what we had A, C, A transpose. So it's like this. H covariance of theta, H transpose, plus the covariance of the noise. And for the cross covariance, we have between theta and x, replace the x with this one, and the cross covariance, theta minus the mean of theta, and this one, x minus mean of the x. And what you get actually is C transpose H. When you have this, you can actually get the values that you need. So the posterior mean and the posterior covariance are obtained using these equations. When you have the mean and covariance of the posterior, on the other hand, you know that noise is Gaussian, theta is Gaussian, H is just a linear function, so this is also Gaussian, and summation of two Gaussians gives you just the Gaussian. So everything is Gaussian. So the posterior will also be Gaussian. So the posterior will also have just two statistics, mean and covariance, and that's enough. So you get the mean based on these two covariances, you get the mean of the posterior, and you get the covariance of the posterior, and you have all the data is necessary for you to get the parameters. So you can have the parameter. When you have the mean and covariance, you have the estimator. So that's the Bayesian linear model. But in every Bayesian estimation, we know that Bayesian estimator is the optimal estimator in the sense that it minimizes the risk. And we know that the Bayesian estimator, when you have something done in a Bayesian sense, you don't need actually to look for whether you have overestimated something or underestimated something, because it's the best estimator, and there is no kind of overestimation. So the reason is that Bayesian estimator tries to minimize the risk. And what is risk? Expected loss of the estimation. So you try using the risk function minimization, you try actually to minimize the expected loss out of your estimation. And that loss can be defined. For example, it can be 0 and 1 loss. If you get the true value, there is no cost, zero loss. If you don't get it, you get the weight of 1. So it's a very hard assignment. If you don't get the true value, give the loss function to be 1. It means that you've lost. And there is a lot of loss that you have to compute actually in your risk. If not, it's 0. You've got it. But there should be smooth loss functions, not necessarily this hard thresholding. It could be a smooth versions. And we have different versions in the machine learning, you can see it. But in general, the definition is like that this risk function should be minimized based on this cost function. So those probabilities that you are actually looking for are weighted by the loss. And the loss is actually a function over the true and the estimate values that you have. Here we actually succinctly show it as this function, j of your estimate. And this should be minimized. One of the best, the most prevalent Bayesian estimators is the map estimator. In the map estimation, you say that the best parameter value, unknown parameter I'm looking for, is the one which maximizes the posterior. That should be the estimation. And we know that the posterior can be written in the form of Bayes formulation as the multiplication of likelihood times prior normalized by the evidence. And you don't need to be worried about this evidence, because here you are just getting the maximum and you have observed x, so p of x is a constant, you can just ignore it. Maximization of this just is equal to maximize the nominator. And it's interesting, if your likelihood function and your prior belong to the exponential family, again, you can apply the logarithm and change this multiplication to summation. And then again, any kind of argument, the parameter theta, which maximizes the right-hand side, is the same answer of this posterior one. And that's called the map estimator. So these were the approaches and the categorization of estimation methods that we have in theory and also in application. So most of the cases we use maximum likelihood or the map estimator or MMSE estimator. And for the case of speech, if you have a prior and you use a prior, MMSE estimator is one of the best. MMSE estimator is one of the best. When you have no idea, it's better to go for likelihood, maximum likelihood. And if you have enough data, it's better to go for the maximum likelihood. Why? Because maximum likelihood is map estimation when the prior is uniform. If you put P of theta equal to 1 or a constant value, there has no value to get it into a maximization problem. And the posterior is equal to, maximization of posterior is equivalent to maximization of the likelihood. So the maximum likelihood becomes maximum a posteriori estimation.
What do you mean by when you put prior equal to 1? That means we are certain that will...
No, uniform. I said the prior is to be uniform. So over the course of the domain of the prior, the theta, it's uniform. So there is no specific theta value which is weighted over the other one.
Mm-hmm.
If they all have the same probability, then this P of theta is constant.
Mm-hmm.
When it's constant, you can ignore it in the maximization, in the optimization problem. Then the left-hand side, which is posterior, is equivalent to the right-hand side as likelihood. So maximization of posterior, which is map, gives the same result as MLE. They give you the same result. Here, the map gives you the same result as this one. Why? Because this is constant and this is constant. You maximize this, is just the same as maximizing the left-hand side, which is posterior.
So in that scenario, which one is easiest to do, map or MLE?
The same. It's almost...
We can do anything, right? If we do one, we will get...
If uniform, then it's the same. If you are doing MLE, you are doing map. And if you are doing map, you are doing MLE.
So I mean, among map and MLE, which one would be the easiest in that scenario?
In this scenario, they are the same. It's the same activity you're doing. The same action is taken. The same computation, the same derivation, everything the same. Just then you can say that I'm doing the maximum likelihood or I'm doing the maximum a posteriori with prior being
Uniform.
a uniform.
Okay.
In many speech enhancement methods, because they don't care about the phase, we have phase and we have the amplitude. When they don't care about the phase, they put a uniform distribution over the phase, and that's why in most of the cases they just use the maximum likelihood. But if you assign something as a PDF to the phase, something rather than uniform, then map results would be different with the MLE result. They come to different solutions.
But in general, MLE should be better, right? Better than map.
MLE is just better if you have lots of data. If not, map is better. If you have a good belief about the prior, map is better. These are the conditions. So you have to look for the conditions before you delve into the problem, to the solution. Whether you have, whether a linear estimation is good enough or not. If not, you have to go for MVUE, even if it's difficult. If linear estimator works well, then you can try blue methods. Or if you want to do Bayesian, you can try map or MMSE, any of these two cases. Or you can go for the Kalman filter, which is an iterative method, or Kalman filter also is not enough. You can go to some, more effort in the computation, and again, an iterative method, for example, extended Kalman filter or particle filters and so on. But particle filter, for example, is a non-parametric method, so it can be computationally more, elaborate. You have to more elaborate than these ones, but you can come up with some solution at least. So these are the general things I could say about optimization. This about the estimation theory. For the details, now you have the leads. You can go through different articles probably, or you can go to the course. And there is a very good book, nice book from 1995 or 1, I'm not sure, from Stephen McKay. So Stephen M.K. He has a very nice book for the estimation theory. It's almost a reference in more than 99% of universities for the estimation theory. They actually refer to this book. It's a very nice book, and you can use it as a reference. It's very simple, written very simple, with too many examples, practical examples from radar estimations, from filtering stuff, from transmission of a signal over the channels and getting in the receiver, different types of the noises, having the prior, without prior, and many other things. Very nice book. Okay, let's go to optimization. Just a brief introduction to optimization. What's the optimization problem statement? In general, when we say optimization, what we are looking for? What are the kind of problems that I have to expect for? We have two types of the optimization problems in general. Constrained versus unconstrained. When we say unconstrained, it's the right-hand side here. You just want to, for example, minimize or maximize. Doesn't, differ. If something is minimized, which is normally based on the minimization, or the negative of that function would be maximized. So here I have shown that if, for example, you minimize for f of x over the course of the x values, is the same as maximizing the minus f of x again over the same course of x values. So minimization and maximization is not that much important, even though in some of the toolboxes, I think minimization or maximization, one of them is simpler, but doesn't, for us, it's not making any differences. That's the unconstrained version. Just minimization of a function over the course of the parameters, free parameters of that function. X is a free parameter of the function. For example, it belongs to the n-dimensional real values. F is a function, and what you want is to get the x value which minimizes this function and is x star. That's all. It's called unconstrained optimization problem. Constraint optimization problem. You have to minimize that function over the course of the free parameters x, but subject to some constraints, and those constraints might be hyperplanes in that n-dimensional domain, or nonlinear hyperplanes, which are called manifolds. Manifolds. Mm-hmm. So manifolds are nonlinear hyperplanes, which are called manifolds. So it depends. Everything, you are to minimize this f of x over the course of the parameters, but constrained on conditions. And these conditions should be one or more. Depends. Some of the conditions are equality conditions. So you need to have, for example, a g of gi means g1, g2, g3 is a function. So one function over these x values to be equal to 0, for example, which is an equality condition. And it means that, for example, that g over the x is a kind of hyperplane if g is linear. Or if g is nonlinear, then it's a manifold. and that should be, for example, equal to 0, is a kind of equality condition or constraint. And if, for example, you say that gi of x for some I values, which g should be linear or nonlinear, is less than a value, less than or equal to a value, that's an inequality condition. So you're specifying the domain of search for the optimum solution. You're specifying that domain of search by these constraints. In the unconstrained case, you don't care about the domain. The domain is just whatever x value can take. That's all. But in this case, you're actually looking for the optimum solution in a specific domain. With that domain is specified by those constraints. So that's the definition of constraint versus unconstrained optimization problems. Some of the cost functions which you are trying to minimize, if you are trying to minimize something, some of these cost functions, normally you try to minimize the cost. Cost is something that the minimum is the better. So sometimes this cost function is actually multimodal. So you have several minimum values. Probably one of these minimum values is the global minimum, but the rest are just local minimums. So in the local area, it's the minimum, but it's not generally the minimum. It's not the minimum that in general minimizes that cost. For that specific case, the search domain, it minimizes that cost function. Here's an example. It's pretty much, for most of the problems, it's pretty much dependent on where you're starting your search. So if you start from some point, initial point, you might come up with this minimum, and for most of the algorithms, they stuck in that minimum, and they can never get out of that. And if you're lucky enough to start from this point, you probably get the real minimum, the global minimum, and if not, you will just stuck into these local minimums, which are not the global minimum. For some other problems, you have saddle points. So you have saddle points with the curvature actually changes the convexity. And it means that even though for this direction, if you go from this direction, from this view, that point is minimum, but from this view, this point is maximum. Such kind of points, these points are called saddle points. So they are not necessarily the optimum solution, but they should be optimum based on some constraints. So it depends on, pretty much it depends on the direction that you take into the problem. These are called saddle points. Minimum in one sense, maximum in one other direction. These are the things that are important. I'm just emphasizing these things. When you come up with some optimization problem, you have to take care of these kind of notions. We have convexity and concavity. Some problems are called, your definition of the problem, the face of the problem, you say that this convex. When it's convex, generally it looks like this. It means that epigraph is homogeneous. So everything, if you, for example, put a line or a plane, every 2 points on that line or plane, they are actually inside the epigraph. So like the bowl case, everything is inside. And this one is actually concave. But this can simply be changed to something convex. But for example, if you have an environment, if you have a kind of search environment, and that search environment looks like this, in 2-dimensional like this. Then it's not convex. Because if you draw a line between these 2 points, there are infinite number of the points thrown away from that epigraph. And the epigraph, you know that if this is a graph, you draw a line, then the epigraph is whatever on the upside of this graph, upside of the line. But here, whatever upside is not inside this environment. There are so many points from here to here that they are thrown outside. That's why this kind of environment is not homogeneous, and that's non-convex. If the problem is convex, as you can see from the shape, it's very good. Why? Because the global minimum and the local minimum, they overlap. So if you're looking for a local minimum, you're also looking for a global minimum. The solution is the best solution, really the best solution. It doesn't matter from which point you start, finally you come up with the best solution. And that's the global minimum. These kind of problems which are convex, they are also fast because they don't need actually to be run from different initial points. But for the case of non-convex ones, which they have, for example, they are multimodal and they have several minimums, you have to start, even though you get, for example, to the minimum, and the algorithm actually starts, but then you have to run from different initialization points in order to make sure that the minimum point you got is actually the global one. Or at least you run it for 1,000 times from 1,000 different initial points, and then you take the one which is minimum in the end. You assume that that's the global minimum, but it might be, again, the problem. So convexity is very important. And we have a software called CVX. There are so many softwares, but one is CVX, Sedumi, and so on. I have used several times these two convex optimizers. This is from Stanford, CVX convex optimizer, very nice and very easy to use in MATLAB. That you can download it whenever you're faced with a convex optimization problem. You can easily use these optimizers, these toolkits. They are fast enough and they work really well.
So how does this second diagram is concave function? I didn't understand that.
That's concave.
This can also be viewed as a convex function because if you draw a line between any 2 points, it will still lie inside the space of the.
That's convex. The other one is concave. For the concave, we have no problem. We have no problem. For non-convex, which is something between convex and concave, it's non-convex. We don't say concave.
Okay.
Everything convex, non-convex doesn't mean that it's concave. No. Here we have a fuzzy meaning of these two terms.
So it's either convex or
That's non-convex, but I didn't say this is convex, concave. I said just non-convex. If it's non-convex, you have problem. It's concave and convex, you have no problem.
Okay.
So, in general, that's I think a very good slide. You can take it forever. Any optimization problem comes into the umbrella of one of these categories. Any optimization problem you have. Well, not to say any, because there are some other methods, integer optimization, or discrete optimization methods. But in general, the optimization methods that we face with in the applications are belonging to one of these categories. These first three categories are dealing with a cost function which is not stochastic. And the last one, EM algorithm, is when you have a random cost function or a stochastic cost function. For the left-hand side, which your cost function is deterministic, it's not stochastic, we have different views. For unconstrained optimization problems, we have line search, one of the basic optimization methods. We have a steepest descent, and in a stochastic version of that, which is called a stochastic gradient descent. You probably face with gradient descent in many, many problems. So it means when you say gradient descent, it means that you have a function, you try to minimize that function over the course of the parameters, x parameters, and you have a vector of parameters. A stochastic gradient descent is just using the first derivative of that function, that f function, which is gradient. And we have Newton method, which is actually a second order, which uses actually the Hessian, which is the second derivative of the signal, of that cost function over the parameters. Then we have conjugate gradient, and we have quasi-Newton methods. And these are just to come up with some problems that occur normally with the Newton method. They came up with some, remedies which are called the conjugate gradient and the Newton method to make it faster and not to stuck in some point that the algorithm stops and cannot go further. These are all the unconstrained optimization methods together with so many other things. I didn't mention everything, so you have a lot of things, but under this category. For the constraint optimization methods, if you have, I just mentioned the convex versions. You have for non-convex versions, you also have something for concave versions. Or for the non-convex versions, you have some other methods. But normally we deal with the convex case. And that's why you see that most universities, they teach convex optimization. Linear optimization and convex optimization, but nothing out of that. Specifically in the engineering departments. But for the mathematical departments, they also go to integer, discrete optimization, and so on. But for engineers, they try to define their definition of the problem, the face of the problem, to actually fit into one of these categories. So for the convex optimization, we have linear programming, simplex and interior point methods, and in MATLAB you have all of them. You have quadratic programming. So quadratic programming is in the case that your function, the cost function that you try to optimize, the minimize for example, is quadratic, the second degree. Linear is linear, this one is quadratic. And you have the method of penalty barriers. You have some other heuristic methods. These are really heuristic because they are taken from some natural phenomena. And they actually, people found it very useful, specifically when you have global optimization problem. If you have global optimization problem, or if you have a plateau. What is plateau? Plateau is, let me draw it here. Assume that your cost function looks like this. That's your cost function. Then you start from some point and assume everything is asymptotically convex. You start from some point here. You're using the gradient descent algorithm, like backpropagation in neural networks. You are designing a neural network, and your cost function is actually a gradient. What you're trying to do is you're actually backpropagating the gradient error to the the previous stages in the neural network. The cost function is actually optimized based on the gradient descent. At least one of the versions, the most prevalent versions, is gradient descent, which is faster than any other method. But the point is that gradient descent starts from some point. If you randomly start from this point and then go further, then your step size start to decrease. And then it takes for a while, quite a while. And how long do you think it will take to come to this point? 1 week, 2 weeks, something? This part of the cost function is called the plateau. And there are methods that are normally used in order to get rid of that plateau, like the genetic algorithm. This genetic algorithm is just based on the, genetics. So what it tries is actually create some samples, randomly creates the samples, spread out the samples, the speeds, and then try to get the minimum out of that. And it's pretty much fast if you, for any kind of optimization problem, which is, has a very complicated cost function, to initialize it with a kind of genetic algorithm or particle swarm, you start with such kind of algorithms from the heuristic methods. And after that algorithm applied for some iterations, then you change it to the gradient descent. Because running one of these as the beginning, as the initialization of the optimization, it certifies that you are around here. Then if you apply the gradient descent, you can directly go to the final point much faster. Instead of running gradient descent from the beginning, you can start from genetic algorithm. The genetic algorithm very fast takes you to this point, and from this point forward you can use it as the gradient descent. In neural network, it's most prevalent to use the genetic algorithm. Then, for example, in MLPs, when you have the multiple layer perceptrons, we'll go back to that. You take one heuristic algorithm like the genetic algorithm or the particle swarm, and then you apply the gradient descent. Also, these algorithms enables us to get rid of the local minimums. So, because they are iterative, if you try, for example, to run this algorithm for some epochs, not just resorting to one epoch, but you run it for 100 epochs, 200 epochs, it's pretty much likely that if you have been in one of the local minimums and not the global minimum, in some other iterations, you're getting out of that local minimum and searching for another local minimum. So these are the algorithms that are helping us, but we have no idea how many iterations. So you have to, if you have time, you can run it for 1,000 times in order to be, to make sure that you're getting to the global minimum. But not necessarily in 1,000 times you will get it. So that part of that is quite, ambiguous. But at least for this kind of things, like the plateau, they really work well. Start with this one, then go to the other one. And this EM algorithm is a very interesting algorithm. In the next lecture, actually tomorrow I think, we will talk about this EM algorithm. It's actually when the cost function is stochastic, it's a random. The cost itself is a random. So it's actually another version of maximum likelihood method when you have some kind of missing data. You know that in maximum likelihood we have P of X given theta. So here you have the observations and you want to find those theta values which maximizes this likelihood function. What if part of this X is missing? Or what if you're actually trying to like the k-means algorithm, to generalize the k-means, to say that I'm not just looking for the mean, but also I'm looking for the variance. So you're looking for an environment, for a kind of, like you're having a bag and you want to fit all the data in that particular bag. So we will come with the examples that I have actually decided to have for the EM algorithm. But EM is a very useful algorithm in the machine learning applications and many machine learning applications. Also, it's for the clustering. So, for density estimation, if you want to, you have a data and you want to actually cluster the data into different clusters, then EM algorithm is one of the best. I mean, intuitively, it's one of the natural things that comes to the mind, but how implemented is actually the EM algorithm that gives us this idea. And let's talk about gradient descent. Just in 5 minutes, we'll finish it actually, because it's just the intuitions and giving the notion, not the details. So what is the gradient descent? Let's talk about the idea in a very simple statement. Optimization problems, when you have several parameters, it means that dimensionality is too high. They're not able actually to, when it's just the one parameter, you just say that, okay, we take the first derivative. Whenever it's 0, you have the stationary point. Whether that second derivative is positive, then it's the minimum. If it's negative, it's the maximum. So simple. What if you have more dimensions, x1 and x2? Then you can go to that minimum point from different directions. If you have multiple dimensions, x1, 2, 3, and n, it's really hard to say that, how should I go to that minimum or optimum point? So the strategy that we take, starting from the line search, the strategy that we take in those unconstrained problems is that start from some point as an initial point, choose your direction, and choose the step that you want to go forward. That's naturally what people do. Let's give a more intuitive example. Assume that there are so many objects here, so many obstacles in this environment, and this environment is just not limited to this, 8 by 7 meters environment room. It's so large, and there are so many obstacles, and I cannot define where exactly those obstacles are and to find the path directly to the point that I want to go, for example. Naturally, what you do, you say that, okay, at this moment, I see that this is the place which is actually looks free. So this is the minimum point that I can actually take my action. I take my step this way. I go to this direction. Then I decide for the next step. You go for the next step. Then you see that, okay, this is close. For the next step. Then start for the next step. And you take these steps until you reach to the point that you want. If there is any path to that point, hopefully you can get it. And you will get it, but how many steps it should take, we don't know. If you take everything in a good way, then probably with less amount of step you can get to the optimal point. Otherwise, probably you need to wait, for example, for 1 week in order to find the right path to go to your optimal point. That's the idea of gradient descent. But what I explained is actually the stochastic gradient descent. And what we talk here is the gradient descent, which says that is based on the fact. The optimum point, the optimum direction to take is the direction which is the negative of the gradient. Why? Because we know that for every multivariate function, gradient, which is the first derivative, gradient gives us the direction of maximum changing, getting the maximum enhancement or improvement. So from any point that you are, if you take the gradient, you're going the way which actually gives you the highest value possible with just the smallest step that you can take. That's the meaning of gradient. So you aren't having a minimization problem, so you have to take the negative direction of that gradient. So take the gradient, whatever direction it gave you, take the inverse of that. conversely go to what the direction the gradient says. It's actually the way that it goes to the minimum. There is a nice example. They say that if there is a hill or a mountain, assuming that it's a mountain, then if here is the ice, for example, when it starts melting, it takes the gradient direction. And it's actually true. Water starts to find the gradient direction to actually go to the lowest level possible, because it's a multivariate case and it takes the gradient direction. So it actually the negative gradient direction. So that's what we take. The negative gradient, the inverse of the gradient, is the direction that we take, but for how many steps and what should be the step size is actually here mentioned. So we say the next point should be the previous point plus the direction and the step size, but the direction is already negative of gradient, and this alpha is just the step size. So the step size times the negative of the gradient. That's what you take to go to the next step, which is xk plus 1. And continue with this until the steps are ignorable. For example, xk and xk plus 1 are almost the same. It means that you have already in the minimum point. That's the idea for the gradient descent algorithm.
But as you said, we can also be in the plateau region, right?
Yes.
So in that case also the Lec8.
If you're in the plateau, then probably the epsilon, if it's, the threshold for the epsilon is really, 10 to the, for example, minus 15, then it will continue running, but it will take forever.
Yeah, so we will not be sure that.
You will not sure. And in order to be faster, you have to take larger steps. But the point is that if you take larger steps and you're almost here, or you don't know where is exactly the minimum point, so you take larger steps, you get rid of the plateau. But the point is that you're here and you're still with the larger steps. You come here, and then the next one, because the step is large, you don't go here, you just go here. And then negative of the gradient goes here, and it starts to diverge. So it's better to have some, there is a analysis for the gradient descent algorithm. So you have always, for this kind of algorithms, you have the analysis of step size. How much that step size should be taken. The optimal step size. So it's very important. You have the direction, but your steps are more than enough. So you take more than enough. Instead of, just going here, stopping here, because of your step size, you go here. And afterwards, the gradient, negative of the gradient, actually shows this direction. It shows this direction, and you're taking large steps, so you are diverging, getting out of the minimum that you wanted. So algorithm actually continues forever. That's the idea of gradient descent.
Is there no possibility if you see first it decreases, then it increases to jump back and to reduce the step size then and do this step again?
Yes, we have variable step size LMS algorithm, which is actually this what we said. It's called variable step size. These are the ideas in the adaptive filters. Adaptive filters, actually, one of the methods in adaptive filters, the intuition behind adaptive filters is exactly minimizing these cost functions. They started with the LMS algorithm, then it started with the gradient descent base, and then they said that, okay, this fixed step size is not good, maybe we have to make it variable. Then they made it variable, then they said that, okay, even if it's variable, but sometimes it happens that because it has an inverse of the matrix in the denominator, it might happen that it's, for example, singularity point, and then it becomes a non-assigned, 1 over 0. That's the problem, division by 0. Then they made it as the normalized LMS, and the block LMS, and so on. So, and then they said that, okay, expectation is a problem, we don't take the expectation, we go through sampling methods, then they actually created RLS method, recursive least square methods. These are all the things that come after this idea. And the final thing, the last slide is just thank you. So the Newton method is a quadratic version of the optimization problem. So it's quadratic because it considers a ball and then starts to make the tangent of the ball with the actually the manifold. The manifold is the function of your optimization, the cost function that you have. So actually it makes the tangent and it gets the value of the tangent. And then continues, if it's a direction, then it continues to the, for the next step again, it continues for the next ball and making a tangent. And if that's decreasing, it means that you're going to the minimum. And if it's increasing, it means that you're already in the landmark and you have changed the curvature. So then you have to stop. For the quadratic programs, it's very good algorithm, much faster. But the problem with Newton method is that because it's quadratic, it actually uses not only the first derivation, which is gradient, but also it needs the Hessian, which is the second derivative. And not only the second derivative directly, but also the inverse of the second derivative is necessary. And that's because it's computationally it's costly. And there are versions coming afterwards because it was really worth to work in it. It's fast, much faster than gradient descent. They tried actually to make different versions out of that. There are functions in MATLAB that you can use for this optimization problems. Fmin unconstrained plus fmin unc. That's all. And you give the function and the domain to search for your minimum. And simply by using the fmin function, which you can just search it in the MATLAB, you can unconstrainedly optimize the problem. Then you have fmin constraint, and you have linear programming method and the quadratic programming method. These are rather than the convex optimizer and many other toolkits that you can just simply install in MATLAB and use it. These are the functions in the MATLAB already set in the MATLAB to be used for. And thank you for your waiting until 22 minutes after the time. But I think that it was worth it to know about these ideas. Then with your problems, when you have real applications, then you can do much better. Okay, if you have any questions, then I'm ready to take them. Okay.